If I knew that, I'd teach it, wouldn't I? Let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day again. I thank you for these students and this class. Just ask you to bless our work today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I will begin with a bizarre calculation. So consider, if I can remember it right, pi cotangent pi z. Let's think about pi cotangent pi z, all right? If you think about that, that's equal to what? Well, that's pi times the what? Cotangent is what? Cosine over sine? So that's, you got yourself a cosine pi z over the sine of pi z, all right? And we can argue that this has a simple pole where? I heard z equals to 0. That's a good start. If I was giving you partial credit, you'd have 0. Because that's one of infinitely many poles. So there's what? There's also plus or minus 1, plus or minus 2, da-da-da-da, right? Z in the integers. All poles. And so, in particular, we can calculate the residue of pi cotangent pi z. All right, at n. And what do we get? Well, we can use rule 3. What? Wait a minute. I don't have glasses, but it seems like something happened. Okay. I don't know what's going on. Like, he's got a baseball cap yesterday. I thought he was like a 15-year-old. Now, I don't know.
Now it looks like I'm 40.
I don't know what's going on. Now you look 40, maybe. 35. Let's see here. So what we got to do is pi cosine, right? Cosine of pi n divided by the derivative of sine, which is what? Pi cosine pi n. So this is by rule 3, right? Using rule 3 to calculate the residue here, we get, well, that's kind of boring. 1. Huh. Well, that's interesting, isn't it? Now, if f is holomorphic, or if you like, analytic, at each n in the integers, then what would the residue of f of z times pi cotangent pi z at n be equal to? So think about this. I don't want to actually do the calculation necessarily, but let me just kind of map out the calculation and explain to you. Really, this is a lemma that I'm going to kind of half prove at the moment. See, we already know that this has a Laurent expansion of like 1 over z minus n, right? Plus stuff. All right. Plus like a0 plus a1 times z minus n, and so forth and so on, all right? But the principal part of it is just what? It's just the 1 over z minus n, because the residue is 1, right? That's the Laurent expansion. How about f of z? Well, we're assuming it's analytic at n, right? So that has an expansion of like, some, let's say k equals 0 to infinity of like b sub k z minus n to the power k, right? So if you think about multiplying that, what do you get? And keep in mind, maybe I'd do better. Oh, I'm sorry, I seem to have just said do better. Whenever I say do better, I just feel dirty. n plus f prime of n times z minus n plus dot 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 dot, right? That's the power series for f at n because it's analytic, right? So when you multiply that, there's only one thing. Oh man. Dodge that. All right, let's see here. So obviously this is just what? The principal part is, f of n over z minus n, right? And then plus da 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 da. Like that's the principal, that's the divergent part of the Laurent expansion, yeah? At n. Therefore, the residue is f of n. So that's pretty cool, right? All right, so let me show you the trick. The trick, if I can find it, is to consider a square that looks something like this. So we've got, here is minus n, and eventually we get that minus 2, minus 1, 0, 1. Let's see here, eventually I get over here to n. All right. Then past that, of course, is n plus 1. And back over here is minus n minus 1, right? And the game to play here is to make a, a contour like that. And specifically, let's see here, going this way. Well, I want to use that color. Here's the imaginary axis. All right, so all right, so we've got minus in down here. You got plus in up here. And then down here would be like minus I n plus 1. And up here you've got I times n plus 1. So it's a little bit beyond n. Let's see here. I'll just do one of these corners. For instance, that one would be n plus 1/2 times 1 plus I. Right. This one over here, for instance, would be n plus 1/2 times minus 1 minus I, all right? So the idea here is this contour is arranged such that it does what? It captures all of the integers between minus n and plus n, all right? Like that. And we're going to make it go counterclockwise like that. That's the curve Cn. All right, so now riddle me this. What if we integrate around this curve Cn and just to save myself some writing, let's define pi cotangent pi z. Let's call that big G. All right, big G of z is cotangent pi z. So suppose we integrate g of z, f of z dz along that curve, right? So then what's the story there? We know the residue theorem, right? So it says 2 pi I, right, times the sum of what? Residues of g of z f of z within the curve Cn, right? But what are those residues? Well, now it begs the question, well, what's f, right? So let us suppose that this f is not just any old function, it is so we're going to assume that f meromorphic it's meromorphic in let's say near Cn. All right, and you know, f let's say non-singular on Z. In other words, I don't want the f to have any kind of poles at the integers, okay? Yeah? So in other words, I'm assuming f is holomorphic at the integers so my lemma would hold. Right? If that's the case, then this we can write as what? Well, this is equal to 2 pi I times what? Times the sum, you know, over n and z, right, of the residue of g of z, f of z at n, plus the sum over the poles of g of z of, you know, the residue of g of z, f of z. And I'll call the pole like z sub I, okay, z sub I, or j, there. All right. Now here's the really cool part. If the meromorphic function is also chosen in such a way that it's bounded, right? If it's bounded in a nice enough way on that square, then what we're able to do is to argue that, you know, for nice f of z, as n goes to infinity, this is trivial. In other words, that goes to 0. Now, what would a nice enough z be? A nice enough f of z? Well, in particular, let me see if I could find you a specific. So here's the statement of the theorem. This is the so-called summation theorem. Let f of z be analytic except for some finite set of isolated singularities, and let me just call those singularities z1, z2, zk, okay? Just for the sake of giving them a name. And also, suppose that the modulus of f of z is less than m over z to the, I guess I shouldn't use k, I better use some other letter. Let's say L, where L is greater than 1. And where is that true? I forgot to say where this is true. For z on where? For z and c inside. I guess, not in, but z an element of Cn, right? For z an element of Cn. That's where I need it. And m independent of n, all right? The bound there needs to be independent of the choice of n. All right. Then we have the following summation formula, namely the sum over n in the integers of f of n is equal to minus the sum. Oh, yeah, I was like, where's the 2 pi I? Can you guys tell me where the 2 pi I is? So the point here is if you have f bounded like that, then you're able to argue by the ML theorem that this integral vanishes. All right? The details are in the handout I posted in terms of why that vanishes. Okay, I don't want to waste your time on that. It's actually not that interesting. Besides, it's probably your homework. And anyway, so because this goes to 0, we just divide by 2 pi I, which shows us that this sum and that sum must be equal and opposite. But the one is the sum n and z fn. The other is minus the residues. Well, it's minus, let me say, sum I equals 1 to k of residue of pi cotangent pi z f of z, comma, z sub I, all right? So this is, I mean, we've been able to calculate oodles of, integrals with this residue theory, but this is something new, right? Now we can actually calculate series, numerical series using residue theory with this tool. And also I should mention, you can, so like this is just why use cotangent? It's just a convenience, right? This trick generalizes. You just if you could find another function which is got singularities at integers, right? And the residues are pretty nice, then that's also useful. Like I think in your homework you explore a different one where you get -1 to the n as the residues of the function that plays the role of pi cotangent pi z. I think it's like cosecant or something does that. So you can swap the g of z equal to cotangent out for other things to get alternating series. This one's good for positive series. All right, like well, let me just actually put this into practice and do a calculation or two. Probably should just do one. Let me skip straight to the one that's actually most interesting. So example 1, suppose you want to calculate the sum n equals 1 to infinity of 1 over n squared. All right. So, whoa. See, I think this is the example I want, but I also think I have to admit it doesn't quite fit. Well, what's the problem? What's the rub? So the terms and conditions of this derivation over here was that the residues of the meromorphic function didn't happen at the integers. But here I'm going to kind of want to look at f of z equals to 1 over z squared for the trick, right? And that is singular at 0, right? So we need to treat 0, we need to throw 0, basically we need to throw 0 into this bucket and leave 0 out of that bucket. So what's going to happen then is we have the sum, you know, over n in the integers, n not equal to 0 of 1 over n squared is going to equal to minus the sum over the residues of pi cotangent pi z, right, over z squared. And so what is the set of singularities, the finite set of isolated singularities for f of z in this case? There's just one. It's 0. So yeah, I'll do one more example. This example is admittedly weird. It's just famous, so I wanted to do it, you know? My bad. So you guys tell me, what is that? We said cotangent has a simple 0, right? If cotangent's got a simple 0 at 0, what does cotangent over z squared have? Yeah, 3, which means we have to do what? We're supposed to do what? So the summation is dumb here, right? I could just erase the sum. There's just 1, right? So we've got minus d dz, d squared dz squared, right? Of pi cotangent pi z. By our residue rule, and we're supposed to evaluate what? Evaluate at z equals to 0, yeah? Oh, wait a minute. What am I supposed to do? For a triple pole, am I supposed to multiply by z squared, or am I supposed to multiply by z cubed? Z cubed. So I'll get my rules right eventually here. Z cubed. So I'm using the residue rule that we derived the other day for the triple pole. So I multiply by z cubed because I'm at 0 for the pole, and the 3 is because I just decided to change pi into 3, which is dumb. Let's pull that pi out. We'll leave it out here where it can't hurt anybody. Now I differentiate once. What do I get? I get 3z squared cotangent pi z, and then minus z cubed times pi cosecant squared, right? Pi z. And I'm supposed to differentiate that, right? Because I got to do 2 derivatives. Now, in the notes I'm holding, he has not done this derivative. He's done a direct series calculation, and I think I'm about to find out why. But let's just stick with it, and I'll admit defeat momentarily. And because I'm supposed to, after all that's done, I'm supposed to evaluate it. Z equals to 0, yeah. So differentiating another time, I get 6z cotangent pi z minus 3z squared pi secant squared pi z minus 3z squared pi cosecant squared pi z plus 3 z squared pi squared. Oh, goodness gracious, no. Sorry, I got to differentiate. Man, why am I not? I should have used these notes. I'm a dummy. Differentiate cosecant squared. What do you got? You've got 2 cosecant pi z, 2 cosecant pi z times the derivative cosecant, which is minus cosecant pi z. I regret this. I regret this a lot. And I don't feel like, I feel like there's a light at the end of the tunnel here, but I think it's a train. See here? I think I am owed myself another pi at the end of all this. Make a pi squared there. I'm supposed to take the limit. Technically, this is all limit as z goes to 0, right? And I think that might actually be a necessary. I don't know. I regret my choices. Well, I guess everything here.
Dr. Cook?
Yeah.
Are we really supposed to have z cubed next to cotangent if we multiply by?
Ah, well, when did you notice this?
A little bit ago.
Why? Why? Come on. Yes. Yes. Yes.
Pretty much as soon as
That is Z. You monster. All right. I hope.
I had to make sure.
It's fine. I'll stay after. I'll just go overtime 10 minutes to make up for it. Just kidding. Mostly kidding. Golly. In the notes that I have posted here, he has the good sense to just take the like the expansion for cotangent pi z and just divide by z squared and just kind of look at it to read off the residue rather than calculating by the rule. That might be easier, but I'm this far in, so here we go. Minus pi, and then I've got what? I've got cotangent pi z minus z pi cosecant squared pi z. And I'm supposed to differentiate that thing. Evaluate it z equals 0, so minus pi, and that gives me a minus pi cosecant squared pi z minus pi cosecant squared pi z. Hey, that's nice. And then plus z pi squared. Ah, hideous. Z pi squared. Twice the cosecant pi z. If I've made a mistake, you're not staying silent right now, are you? There's not like, this isn't some sort of like double super jeopardy. Let's see how much time Dr. Cook will waste today kind of thing, is it? Anyway, I think that's it. Now, now, technically, we're supposed to take the limit, I think, as z goes to 0. I need to remind myself what's cotangent. Cosine? Yeah, cosine pi z over sine pi z. Okay, so cotangent of 0 is not defined. Cosecant of 0 is not defined. Golly. What the what? How is that a thing? Man, this feels very divergent to me. Because I've got a cosecant squared and a cotangent.
What about the z next to them? Like the z multiplying?
Yeah, that helps, but
Do we use L'Hopital?
I suppose, but that doesn't, I don't. Well, this is not the point of this lecture at all. Stupid thing. You know, you're preparing for class. You look something. Oh, okay, yeah. All right, so maybe I should make this a problem for you guys to work out. Cotangent pi z over z cubed. It turns out this is equal to 1 over z cubed minus pi squared over 3z. Now that is obviously not something I've shown, but I am tired of spending your precious class time on this particular calculation, so I'm going to stop there. All right? You got to know when you're beat. So my apologies. But a straightforward calculation that you would welcome as a homework problem compared to the ones I just assigned you, right? Like this is infinitely easier than problem 134 unless you, well anyway, I'm not talking about problem 134. I will not. So this is minus, what's the residue? Well, the residue is just pi squared over 3, right? And how that is shown is in the PDF I posted, okay? He just basically divides the power series for cotangent to find that, right? And the power series for cotangent you can derive with like, division of series or any number of ways. But look at this. See this on the flip side, because this is even, we could write that as twice the sum n equals 1 to infinity of 1 over n squared, right? And so there you go. The sum n equals 1 to infinity. And my bad. Minus, a minus is a plus. Thank you. And so we've got the sum of 1 over n squared is pi squared over 6. And there you go. So that's why the p equals 2 series sums to pi squared over 6. Which is something that you probably can't derive using regular calculations in Calc 2. The proofs I know of this either involve what we're doing right now or Fourier analysis. It's relatively easy to derive from a Fourier analysis calculation. All right. So I will do one more of these and then cease and desist from this business. If I had any good sense, I'd probably stop right here. I'll probably regret that statement later today. But I hate to leave it on the note of that last example. This one's more interesting because it's actually got some singularities which are not integers. All right, so suppose, example 2, you want to calculate like the sum n equals 1 to infinity like 1 over n squared plus a squared, all right, where a is a real number, all right, not equal to 0, let's say. Since we just did the a equals 0 case in example 1, right? So let's not do that. So here we think about f of z equal to 1 over z squared plus a squared, right? And of course that's what? 1 over z plus ai, z minus ai, yeah? And so the residue of f of z, oh, hold on a second. Let me not be dumb. So let's use the summation theorem. Summation theorem tells us what? Summation theorem tells us that, now is this nice enough? Well, this is like 1 over z squared, so it is going to, you can bound that thing on the rectangle, okay? It's going to satisfy that condition just fine. So we can apply the theorem, and what we get then is the sum over n in the integers of 1 over n squared plus a squared is equal to, all right, so we need what? We need the residue, well, minus the residue of, how's it go? pi cotangent pi z over what? Z squared plus a squared? Where? At ai minus the residue of pi cotangent pi z over z squared plus a squared at minus ai. Do you guys agree? I think that's what we're supposed to do here. So there's only two singularities for f, right? This time. And so we just need to calculate these residues. But since ai is not an integer, we have that, cotangent pi z is, it's holomorphic at like plus or minus ai, right? Which is to say that we can use rule 3. Yep, rule 3 is the one. And that's going to give us minus pi cotangent pi ia divided by derivative of that is 2z, so I get 2 ai. And then minus pi cotangent of minus pi ia. Yeah, I can't talk. 2 times minus ai. Right? And 3 minuses, cotangent's odd, right? So altogether we got ourselves a minus pi cotangent of pi ia over ai. All right? There's a typo in the posted PDF here, by the way. He's got like a half in this answer. It's not supposed to be there. Because they combine half plus a half is 1. And if you look on, he'll see that he corrects the error in about a half page. But anyway, here, we can switch that, right? How does cotangent relate? What is cotangent? So if you got like cotangent of, let's say, I theta, that's what? That's, I just had it over there. What was it? Yeah, cosine of I theta over sine of I theta, right? But what's that? That's cosh, right? That's cosh of I theta, isn't it? Or cosh theta. And this is what? I sinh theta, right? So, in other words, it's coth of theta divided by I. And so you got minus pi coth of pi a divided by I ai. I squared is minus 1, so you got yourself a pi over a hyperbolic cotangent of pi a. And then we simply use the usual trick, right? If you think about even and you think about negative and positive integers, this is an even function of n, right? So by just calculus 2 stuff, really, I don't know, just common sense, honestly. That's twice rather. The sum n equals 1 to infinity, 1 over n squared plus 1. Now that's not quite true, is it? That's not quite true. What is it missing? I'm talking about the positives and the negative. What's in the middle? 0, right? So this doesn't account for, this gets the positive, it gets the negative, but it doesn't account for 0. 0 is what? 1 over a squared, right? So there you go. This is equal to that. And so lo and behold, we have the formula that the sum, n equals 1 to infinity of 1 over n squared plus a squared, all right, is equal to, what's it equal to? Well, pi hyperbolic cotangent of pi a divided by 2a minus 1 over 2a squared, right? Did I get that right? So I subtract the 1 over a squared to the other side, and then I divide it by 2. There you go. It's kind of nice, isn't it? I wonder what would happen if we differentiated with respect to a. What would that give us? It would give us what? 2a over n squared plus a squared squared? Yeah. Wait a minute, is there a minus because I'm differentiating a reciprocal? I should have a minus, right? And that would be equal to what? Pi, what's the derivative of coth? I think it's squared pi a. There's a pi squared here. Oh, great, googly moogly. Well, I don't want to commit to that, but I'm not committing to that, but DDA of the above, all right? Wait, what am I doing? Pac-Man. I wonder if that's true. What do you think? Can you differentiate that formula and get a new formula? I bet you can. I bet that's another series formula. See, when you derive a series formula that depends on a parameter in a smooth fashion, well, you can do these kinds of things and get new formulas. Also, which might be interesting, is to take the limit of the expression above as a goes to 0, and see if you can't derive pi squared over 6 from this. I don't know if that's legitimate or not. That's riding the line of what's maybe going to get you into trouble. All right. All right. Anyway, so I just wanted to expose you to this wild world of bizarre series calculation. There's like a 4 or 5 problem stretch in your mission 8, which is on these. Basically, those problems develop this theory and then apply it. So I'm pretty sure the PDF I've posted essentially has probably how to solve at least a couple of those problems. I haven't looked at it for sure, but I think so. All right, let me go on here. If I can, yeah. So next we need to talk about the argument principle. We've got argument principle 1, argument principle 2, and what's called Roche's theorem. And Roche's theorem is proved with the argument principle. All right? And the argument principle is, this is chapter 11 in my notes, right? Let me give you a definition here. 1 over 2 pi I integral over gamma of f prime of z dz over f of z, all right, which is equal to 1 over 2 pi I, the integral over the differential of the log of f of z. In some sense, this is a definition. All right, like this is defined here, okay? You got me? Yeah. This is the logarithmic integral of f of z along gamma. All right. What does it do? I said essentially the logarithmic integral measures the change of the log of f of z along gamma. So what is the log of f of z equal to anyway, guys? Well, it's equal to the natural log of the modulus of f of z, right? Plus what? Plus I times arg of f of z. As we've remarked earlier, if f of, well, let's think about it this way. If f of z is, holomorphic, let's say, right? If f of z is holomorphic, then natural log of f of z is what? Natural log of the modulus of f of z is, how can I say this? So if I take the differential like this, right? So you got differential of the natural log of this plus I times the differential of the arg. Now, I'm being a little bit hand-wavy here at the moment, honestly, guys. But we will derive these things as the section goes on, okay? I just want to tell you where it's going. What happens if you integrate around a loop this quantity? What if gamma's a loop? What if it's not just a curve? What if it's a curve that, starts and begins at the same point, right? Think about it. This piece is going to integrate to 0 because essentially natural log of the absolute value of the modulus of f of z serves as an antiderivative for that integral. Anyway, that integrates to 0 because it's a total differential. And this, I would love to say integrates to 0 because it's a total differential, but we know the rub, right? Arg of f of z, we can't continuously assign the argument all the way around the loop. So that's got to have a jump. So basically, when you integrate this, when you take this integral along a loop, this piece drops out, and you're just calculating that. So essentially, just calculates angle, like change in angle in some sense. But we're dividing by 2 pi I, so it's not right that, right? So if your change in angle goes 2 pi, right? And you got the I there, so the I's cancel. So if you change an angle 2 pi, well then this just gives you 2 pi over pi, which gives you 1. If you go twice around, this integral gives you 4 pi divided by 2 pi I, divided by 2 pi, which gives you 2. So what this is going to do is count the number of times, count the number of times that you go around. Well, that's not quite what it does. But anyway, let's talk about what it does. So example 3. Let's calculate this integral. And you've had homework on this integral, haven't you? This looks familiar, doesn't it? So what if we take f of z equal to z minus z naught, let's say to the power n, all right? And let's look at the circle centered at z naught, all right? And radius r. But instead of doing what we usually do, which is just covering the circle once, let's cover it k times. Right? Let's cover the circle k times in the counterclockwise sense. Now, what does that mean? Here's k equals 1, right? Like that. Here's 2, right? And 3. Well, you get the idea. We just keep going round and round and round and round k-fold times, right? If k equals minus 1, that would be a clockwise turn, right? Now, but I'm just going to do it for positive k, okay? So, okay. Sorry, I'm an idiot. So the parameterization of the circle, as we've known for some time now, is what? It is z naught plus r e to the it, and here's where we get the k-fold covering, 0 less than or equal to t less than or equal to 2 pi k, right? If I put k equals to 2, we go 0 to 4 pi, k equals to 3, 0 to 6 pi, so forth and so on, right? So what is f prime of z here? It is n times z minus z naught to the n minus 1, right? And so what is, what if I divide that by f of z? What do we got? We get what? N over z minus z naught, yeah? And so if you calculate 1 over 2 pi I integral of f prime of z dz over f of z here, we're looking at the integral 0 to 2 pi k, 0 to 2 pi k. What is dz? Well, dz is I r. Well, actually, guys, let me not be a dummy. Let me just do this. Fine. I don't know. I'm kind of like, I kind of want to just go back and refer to your early homework problem and say, we integrate the reciprocal function. You get 2 pi, but you do it k times, so you get 2 pi k for the integral. But let's do it. I r e to the I t dt, that's my dz. And then my, of course, the f prime over f just leaves me, I got an n from that, from the differentiation, right? And z minus z naught, well, that's just r e to the I t. So the r's, they be canceling, e to the I t be canceling. I forgot about my, what I neglect. Preston probably noticed this when I did it, and he's just been holding it in, not letting me know about it. And I understand that's his way. Remember that and grade the next test and see here. So ni divided by 2 pi n. You guys assume I'm not a petty person, but maybe you assume incorrectly. Maybe I am petty. Maybe I've just been waiting for the right time. The most hilarious time to exercise my pettiness. I think we've got a, dt, yeah. So hopefully that integral we can do, right? So the i's, they be canceling, and we've got n over 2 pi times 2 pi k, altogether nk. What it is?
What?
You just looked happy.
No.
Oh, okay. You just love math. You just love.
Confirm that Jack loves math.
You can confirm that Jack loves math. But does math love Jack?
Yeah, for math. He gets over 100 on every test.
But my tests are out of 150.
They're at 175.
Yeah, it varies. I can't remember. All right, are we good? This is an example of the logarithmic integral. What's it doing? It's counting. What has it done? It's counted. So like if you look at this function, it has a 0 of order n, right? And so the logarithmic integral, it's counted that it has a 0 of order n. But then this k here, well, this k, I'm not going to talk about k much more. Like I'm pretty much done with it. I've got it out of my system here. But k is equal to the winding number. And there's a more that could be said about winding number in here, I suppose. Pretty much all of the theorems that many of the theorems we've done, I've stated for like a curve that's covered just once, right? But if the curve was covered twice, then you basically take what we had and multiply by 2. If you covered it 3 times, you multiply the integral by 3. This just comes essentially from the additivity of integration, but a lot of the theorems that we write in here, we could write for multiply covered loops, and we just end up multiplying by the winding number. There's a story to tell there that I've only told in part. And so, anyway. But actually that's kind of a useful thing to have on hand here, because when we get into the calculations which follow here, we end up having curves which are like winding around a given path more than once, and that's kind of part of the discussion. So I guess I can't entirely stop talking about it. I'll try to emphasize when we get back to it again, though, okay? So what's up next here is the argument principle, which is essentially just a generalization of this theorem. And so theorem, let me make sure I state it correctly. If this is argument principle 1, argument principle 1. It says let D be a bounded domain with piecewise smooth boundary D, and let F be meromorphic. What's that mean? Meromorphic function, meromorphic on D, that extends to be analytic on the boundary of D, such that f of z is not equal to 0 on the boundary of D. All right. Then the logarithmic integral, what's it calculate for us? 2 pi I integral of the boundary of D, f prime of z over f of z dz is equal to n sub 0 minus n sub infinity. What is n sub 0? N sub 0 is the number of zeros inside D. All right. Put my marker. N sub 0 is the number of zeros inside D, counting multiplicity, right? And n infinity is the number of poles, where we say, for example, a simple pole counts as 1, a double pole counts as 2, triple pole counts as 3. You get the idea? So, the number of zeros, number of poles, both, of course, inside D. So, like, roughly speaking, you can kind of picture it something like this. Here's my D, right? And I don't know, let's say Z1, Z2, Z, how many zeros do you want to have? Let's say ZR. These are all zeros. And let's say that like Z sub j has order M sub j, all right? And then poles, let's say P1, P2, PS. All right, these are singularities for the function, all right? So let me say that P sub k has a pole of order n sub k, all right? Then this, in that notation, would be the sum j equals 1 to r of m sub j minus the sum k equals 1 to s of n sub k. All right, that's explicitly what I mean by this, all right?